College Algebra, Chapter 5, Section 1, Inverse Functions. Okay, inverse operations are operations that undo each other. For example, addition and subtraction. If you take x and you add 3 and then subtract 3, you're right back to x again. Multiplication and division. 2 times x divided by 2 leaves you with x. Powers and roots. We all know that when we want to solve for x, if it's under a square root, we need to square both sides. If it has a square on it, we need to take the square root. And then logarithms and exponentials, which we will be getting to. All right, so let's say f of x equals 8x and g of x equals 1/8 x. Then f of 12, so 8 times 12 is 96. And then g of 96 is 1/8 times 96, which is 12. Notice what we did there. We put in 12 for x and f. We got an answer of 96. And we took 96 and put it in for x in function g and got 12 back. In other words, g of f of 12 is 12. Also, you could do this and try it out, see that it works. If you do it the other way around, if you do g of 12 first and then put that answer into f of g of 12 will also give you 12. That means that these two functions are inverses. For these functions, it can be shown that for any value of x, f of g of x equals x, and g of f of x equals x. And like I said, that means they're inverses of each other, because when you do one to x, and then you, right after that, do the other, you get back x. A function is one-to-one if, for elements a and b from the domain, a not equal to b implies that f of a is not equal to f of b. All right, what that means is that each unique x value produces a unique y value. In order to be a function, every x can have exactly one y. However, multiple x's can all produce the same y. For example, the equation, y equals x squared. If I put in 2 for x, I get 4. If I put in negative 2 for x, I get 4. And that's okay. It can still be a function. A one-to-one function is one where the reverse is also true. Every x value can only have one y, and every y value can only have one x. So the function y equals x squared would not be considered one-to-one. And only the functions that are one-to-one have inverses. Now you're going to decide whether each of these functions is one-to-one. Pause the recording, give it a try, and resume the recording to check your answer. Okay, so A is not one-to-one, and the reason for that is, pick a number such as 3. If you put in 3 for x and you put in negative 3 for x, you're going to get 4 for both of those x values. That's going to work with any pair of opposite numbers with opposite signs. 4 and negative 4 will produce the same y value, So it's not one-to-one. Now part B, it's a little harder. I mean, you could kind of do it the same way. You could try numbers with same number with opposite signs. You'll see that you get two different answers. What they did was they said, all right, well, let's just use A and B. If A is not B, then negative 4 times A is not equal to negative 4 times B. So negative 4A plus 12 is not equal to negative 4B plus 12. So kind of doing a little bit of a proof with that. But the end of that is that for B, it is a one-to-one function. Now the horizontal line test lets us check to see if a function is one-to-one by graphing it. We know that to test to see if we have a function, we can use what's called the vertical line test. The vertical line test is where you can draw a vertical line anywhere, and it will only connect the graph, the curve, at one point. If the horizontal line test is to use on functions to see if the inverse of the function is also a function. In other words, if it's one-to-one. So here's the horizontal line test. You draw a horizontal line through the graph of the function, and if the horizontal line intersects the graph of the function in only one spot, at no more than one spot, then the function is one-to-one. And in case you haven't picked up on it, the idea of one-to-one is that the original equation, the original relation is a function, and its inverse is also a function. So that's what we're checking for. Okay, we're going to use the horizontal line test to determine whether the graphs are graphs of one-to-one functions. And here's our first one. And you could tell that this is not one-to-one. There's a red dotted line that goes through, and it actually hits it in 3 points. This is not a one-to-one function. B, on the other hand, is one-to-one. No matter where we draw those red lines, we're only intersecting the line at one spot. So let f be a one-to-one function. Then g is the inverse function of f, and f is the inverse of g if, when you compose them, f of g of x, you get x for every x in the domain of g. And now we're reversing it, g of f of x equals x for every x in the domain of f. In other words, like we said earlier, if you can compose two functions and the result just gives you x, then those two functions must be inverses of each other. So you're going to show that x cubed minus 1 and the cube root of x plus 1 are inverses. What you're going to do is you're going to compose the two functions. Now you need to do f of g of x and g of f of x to show this. Pause the recording, give it a try, and resume to check your answer. Okay, so we've got them composed here, and this can look a little intimidating, but because they're inverses, everything drops out really nicely. We take the cube root of x plus 1 and we cube it, and then subtract 1. That gives us x plus 1 minus 1, which is x. Doing the composition the other way, we have the cube root of x cubed minus 1 plus 1. Well, the minus 1 and plus 1 cancel out, so you have the cube root of x cubed, which again is just x, which means that these two functions are inverses of each other. Now we're going to look at how to find the equation for the inverse of a function. First of all, the notation for an inverse is the name of the function, like f, with a little minus 1 superscript. Now that does not mean f to the negative 1 power. It does not mean to put it 1 over it, and it's read f inverse. Now by the definition of an inverse function, the domain and the range are going to switch. So the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. So we're flip-flopping them. And this is kind of a visual of that. Okay, the domain of f becomes the range of f1, f inverse. The range of the original becomes the domain of the inverse. So we're going to determine whether these two functions are one-to-one. Now these are just lists of points. They are functions, and you want to figure out, is it one-to-one, and if it is, then what is the inverse? Pause the recording, give this a try, and resume to check your answer. Okay, so for A, each x value has just one y value, which is what makes it a function. However, we have a y value that belongs to two different x's, 1, 2, and 2, 2. We can't have that. Also, negative 2, 1, and 0, 1. So that means that the inverse is not a function. That means this is not one-to-one. And since it's not one-to-one, we don't need to find the inverse. G, on the other hand, is one-to-one. You'll notice every x has only one y. Every y goes to only one x. And this is probably the easiest type of thing to find an inverse for, because all you need to do is just switch out the x and y values of the points. So 3, 1 becomes 1, 3, 0, 2 becomes 2, 0, 2, 3 becomes 3, 2, and 4, 0 becomes 0, 4. Now for a one-to-one function defined by an equation, we're going to find the equation defining the inverse as follows. First thing we're going to do is we're going to interchange x and y. Second thing we're going to do is we're going to solve for y. And then we're going to replace the letter y with the f minus 1x, with the f inverse symbol. Notice that at the top there it says any restrictions on x and y should be considered, because if there are restrictions on the original, they're going to be restrictions on the inverse, but they're going to be in the opposite. So any restrictions on the domain of the original become restrictions on the inverse, and any restrictions on the range become restrictions on the domain. So we're going to find the inverse, if it exists, of f of x equals 2x plus 5. We want to start by writing this as y equals 2x plus 5, swap x and y, and then solve for y. Pause the recording, give this a try, and resume to check your answer. So we have y equals 2x plus 5, then we switch the x and y, and we solve for y. Subtract 5 from both sides and divide by 2, and then finally replace the letter y with the inverse function for x symbol. All right, so what does it look like graphically when we have an inverse? Well, if f and the inverse of f are inverse functions and f of a equals b for real numbers a and b, then the inverse of b equals a. In other words, again, the x and the y values are going to swap. That's what this is saying, just like we've seen before. In other words, if the point AB is on the graph of the function, then the point BA is on the graph of the inverse. If 2, 3 is a point on the original function graph, then 3, 2 is going to be a point on the inverse. If a function is one-to-one, the graph of its inverse is a reflection of the graph of f across the line y equals x. So this is what we're looking at. In red, you see the line y equals x. We have the point AB, which was in the original function, and its reflection is BA. And notice how, that inverse, the BA, is exactly a mere reflection of AB across the line y equals x. If you were to fold that graph on the line y equals x, those 2 points would match up exactly. All right, finding the inverse of a function with a restricted domain. We got f of x equals square root of x plus 5, and we need to find the inverse. You need to remember that we don't want a negative under a square root. So the first thing you need to do is determine the domain and range of the original function, because this is also going to feed into the domain and range of the inverse. Pause the recording, give this a try, and resume to see how you did. All right, the domain is restricted to -5 to infinity, because these are the numbers that are going to give you a positive, or a non-negative rather, value under the square root. The range would be 0 to infinity, and you can confirm that by graphing it. It is one-to-one, and it does have an inverse, so we write y equals square root of x plus 5. We switch the x and y. We square both sides and subtract 5. So the range of f is the domain of the inverse. So the range of the original function was 0 to infinity, or x is greater than or equal to 0. So our inverse is x squared minus 5, but x has to be greater than or equal to 0. Now we're going to find the inverse of a rational function. These can be a little bit of a challenge, but I want to encourage you to pause the recording and give it a try, and then resume to see how you did. The nice thing about the rational functions is that once you've figured them out, they tend to all work the same way. So we started like we start any other inverse. We swap the x and y out. So we have x equals 2y over y minus 1. Our natural inclination is to get rid of the denominator, and that's a good idea. So let's multiply both sides by y minus 1. And then we're going to distribute. So we have xy minus x equals 2y. Now what we want to do is we want to get anything that's got a y attached on one side and anything without a y on the other. So we're going to subtract 2y from both sides and add x to both sides, and that gives us xy minus 2y equals x. Now factor out the common factor of y, and we have y times x minus 2 equals x, and then divide. Like I said, it's a little bit of a challenge at first, but when you understand that they pretty much all work this way, it gives you a pattern and you can get them every time. So the inverse is x over x minus 2. Some important facts about inverses. If the function is one-to-one, then the inverse does exist. The domain of the function is the range of the inverse, and the range of the function is the domain of the inverse. If the point AB is on the graph of f, then the point BA is on the graph of the inverse. So the graphs are reflections of each other across the diagonal line y equals x. Now, one application of inverse functions, or really a lot of different mathematical things, is actually coding stuff, putting things into code. So what we're going to do is we're going to use the one-to-one function f of x equals 3x plus 1 and the values in the table to code the message play my music. What you're going to do is you're going to take each letter like P. The number for P is 16. You're going to put that in for x and get a new number for 16 for P. And you're going to do that for every letter in the statement. Pause the recording, give it a try, and resume to check your answer. So play my music would look like this: 49, 37, 4, 76, 40, 76, 40, 64, 58, 28, and 10. And they show you why, because P corresponds to 16, 3 times 16 plus 1 is 49, and so on. Now the rest of this is just extra practice, so what you're going to do is you're going to try these problems, pause the recording to do that, and then resume to check your answer and do that for the rest of the recording.